Hello. I think no one else has joined, so let's wait. Hi, Sarang. Just wait for 2 minutes.
I'm Brahmik.
See if anyone
Okay,
else will join.
okay.
Okay. I see Rohi has joined in as well. So let's give it a start. Let me just share my screen and we can start from there. Okay. So I hope you can see my screen as well, right? So we have already looked into briefly into binomial and Poisson distribution with a couple of examples. I am here to share the Wikipedia pages, but I'm sure you can yourself also go to Wikipedia and have a look. But I'll share some more pages which will give you some good insights on what these distributions are, or maybe where they can be used and so on. So now we have just one main distribution left. This is not the only distributions which can be possible with respect to the data that we have already discussed, but the last one is the most important one, and the goal of any analysis or any situation is to bring these two distributions which we have into a normalized form. And what I mean by normalized form will be clear right now when I talk about the definition of this kind of a distribution, which is known as a standard or a normal or a Gaussian distribution. Right? This is a very important kind of a distribution because it gives a rise to a parameter known as z-score, and we will be specifically using z-score later on when we are going to do statistical inferencing. Right? It's going to be useful in case of, let's say, machine learning as well, in cases, and specifically helps while doing the data analysis part of things, especially. Now, before we look into the definition, I would like to clarify that in different areas, in different books, standard distribution is described in a different way, normal distribution is described in a different way, and Gaussian distribution is described in a separate way, right? But overall, the ideology or the idea, the principle that they all have is that Uh, this is such a distribution where we have a perfect bell-shaped structure of the PDF. So if I draw the PDF, I hope you remember PDF is equal to probability density function. Okay, so probability density function, if I'm drawing that for any random variable, so I'll take any random variable x, which let's say constitutes of, let's say, real number, so it's part of the set R, right? And let's say it can range from anything in the range of, let's say, minus infinity is greater than, is less than or equal to x, while x is less than or equal to plus infinity. So this is the range of the random variable x. So it can take any value, any real value or any standard value between minus infinity to plus infinity. That is its range, and it's part of a set of real numbers. Then if I try to draw, let's say, the distribution, the PDF of that random variable x, then maybe, okay, if I'm lucky, then I will see something like this. So maybe if I'm lucky, I'll see that the distribution goes up and then it's simultaneously comes down. Although I did not draw it in a very good way, but the intention here is that if I break this graph into two halves, so if I distribute or if I divide these PDF, this probability density function, okay, into two parts right at the peak. So this is the peak. I have only divided this chart, this curve, into two parts. So this is one part and this is one part. The curve is exactly similar to each other. So let's say that if let's say this thing is drawn on a piece of paper, okay, if this thing is drawn on a piece of paper and I fold it on this place, then this part is going to exactly overlap on this part, right? Because they are entirely symmetrical. This side is entirely symmetrical to this side. The growth as well as the decline. So here I have seen the growth, here I have seen the peak, here I have seen the decline. This is entirely symmetrical to each other. The rate of change and everything is all same, right? So if let's say I take the value which is at peak, okay, which is something like, let's say, y1, okay, because this is y-axis, so I'll take this is y1, and then I take a value over here, okay, so let's say this is y2. So this intersection of y2 happens on this graph at this point and at this point. So the difference here, let's say this is d1, and the difference here, let's say this is d2. Okay, this is the real difference. So I'm just trying to measure this. Okay, so this is exactly the same on both the sides. So if I, let's say this value over here is x1, okay, or xi, then at xi, which is the peak point, I take a difference of any point y2, and then this value is going to be exactly same as this value. So there is no difference between each and every section which you draw, howsoever small or big that section might be. So the rate of change as well as the shape, structure, everything is the same. Now we have already seen one case which is similar to this, where we had a structure similar to this one. So we already know what happens when we have a proper bell curve, but just to repeat what we already know, if I take this peak value over here, then this is where I will have the mean, the median, and the mode. So everything falls at this point only, right? Everything is here, irrespective of whether I'm drawing a PDF or whether I'm drawing a simple distribution of the values. Even if I draw a simple distribution of the values, in this case, this curve over here is just a simple distribution, the standard distribution, or it is just a plot of the histograms, right? So if I plot that of the histograms, but this is then becomes a PDF, right? So irrespective of what kind of distribution I try to draw, it always comes like this, right? But it's not the case when I draw a cumulative distribution. So in case of a cumulative distribution, it's going to again follow a very symmetrical kind of a structure, right? Because as you see in this part represents this increase, and then the decrease is also similar. So this is the peak point, okay, and then I have a decrease. This section over here is exactly same as this section over here. So this is the essence of a normal distribution, where mean is equal to median is exactly equal to mode, right? Now, it is a very ugly function which defines the PDF. I'll share you the function at later stage, maybe on email or maybe on our LMS itself. I'm going to share a small photograph which is going to give you the formula. The formula is very, very difficult to remember, but I can assure you, you don't have to remember. The reason why you don't have to remember is because there are already functions available in Excel or in R and Python which can help you draw the probability density function, which we'll see when we do the coding, right? So we'll see that. So when we create such kind of plots, we already have ways to create the probability density function. So we don't need to remember the formula, but it is to tell you that yes, there is a formula, and that formula, other than the constants or other than each and every value that X can take. So for example, in the chart that I have drawn right earlier. So if I have a probability density function of a random variable X, which is something like this, then it's a range. Its life cycle is taking a lot of values, right? In its life cycle, it is taking a lot of values. Okay. Now all of these values is what I need. I need each and every of those value, which I will get anyways, because if I've sampled the data, if I've actually collected the data, then I know what is or what are the values, because that's how I have created the histograms, right? So I know the values, that's all I need. And then I need to calculate this value. I need to calculate this value. This value, I will call this a mean, or usually statisticians are going to call this a mean. However, basis the nature itself, nature of the normal distribution or a Gaussian distribution is where mean is equal to median is equal to mode. So in this case, we are going to call it mean, okay, because we should consider this as a probability density function, and that is the reason why we should take this value as a mean. It can be called a mode or a median as well. So if you are writing this value, this peak value, not as a mean, but also as a median or also as a mode, it's all fine. Now, what I mean or why I'm stressing on this mean value is because in the function which I have, I am going to use this mean, and I'm also going to use the spread, and that is the reason why I tried to explain the rate of change using those y1 and y2 values, because the rate of change on each and every side is going to decide what is the variety of the data, right? How much varied the data is. So we know that the variety or the variability of the data is defined by variance, which is given by sigma square. Or if I take a root of that, right? If I'm going to take a root of that, I'm going to get the standard deviation, which is the sigma. So in this case, in case of a probability density function that belongs to a normal distribution, which is like a bell curve, I'm going to consider the variance and I'm going to consider the mu. Basically, if I take a function, or if I would like to simply define what is uh, the probability density function, or how the probability density function is created when it comes to normal distribution, then I can simply say it's nothing but a mathematical function other than the constants using the mean and the variance of the data. So I have a random variable x, which is part of real numbers. I simply calculate the mean and the variance, and then I should be able to understand the probability density function by fitting those values inside a mathematical formula. Okay, so the mathematical formula uses two constants, one which is the value of pi and one which is the epsilon. Now this is not the uh, uh, this function, this Euler's constant that we have seen, right? This is not the Euler's constant. E in this case is going to be the exponent, okay, or the exponential. The exponential is basically out of the box log. Okay, so it is the logarithm. It is the opposite of the logarithm that creates the exponents, and that's what we are going to use. E in this case does not mean Euler's constant that we have seen earlier. Okay, so please don't get confused. Euler's constant was only applicable when we looked into Poisson distribution. Now, and yes, of course, I'm going to share the formula later on. What is, or what are some of the properties? Okay, so what are some of the properties that we have of this distribution function? So the first property is this. This itself is a property. Mean is equal to median equal to mode. The graph is symmetric across the mean. Right, so in the middle part you have the mean. So if this is the middle part, you have the mean, and then on left side, on the right side, you have the same kind of graph, you have the same kind of structure and so on. Right, so that's why it is symmetric across the mean. Right, if I would like to do something funny, let's say I have a graph which is like this. I have a normally distributed variable which is like this. What if I want to take values beyond this point and values beyond this point as well? If I take values beyond this point and this point, then I will see that this line over here is actually running in parallel to the x-axis. If this is the x-axis, any point I take after a certain point in time, after the graph has really formed the bell shape, I can call these are the endpoints. Okay, these are the ends. These are the two ends of this normal distribution. And then anything I take beyond this is always going to be a parallel, or always going to be parallelly constant, or the value will be parallel to the x-axis. Okay, this is a very important uh, concept. Why? Because irrespective of how many values you take, if it is a normal distribution, then if the tails of the distribution are extended, okay, beyond a certain layer, or let's say beyond a certain limit, then they will run parallel to the horizontal axis or the x-axis, right? Then I have another property. The property is what I have already told you in form of a function. The function, or the probability density function for the random variable x, is simply going to be a function of its mu, or its mean. So I'll say mu and sigma square. Right, I don't have these signs on my keyboard, so that's why I'm going to write it like this. So it's a function of mu and sigma square. Okay, it is not a function of the standard deviation directly, but indirectly it's a function of the standard deviation as well. Right, we are going to see how it is the case, or why it doesn't matter whether I write the sigma square or whether I write this thing as equal to something like this. If I replace this and call this standard deviation, it's also going to be the same thing. And we will explore why this is the case. Statistically, we have to define a standard normal variable first, and then we can define the fifth rule. So first of all, we will define a standard normal variable. Okay, this standard normal variable is given by the letter Z. Okay, there is a very peculiar concept behind this. Z is given because it represents the end of the character line. The A to Z is the regular characters that we have, right? Beyond that, we don't have any characters. Beyond that, we only have, let's say, I don't know, the special characters or other ASCII characters. So Z letter represents the end. So what did we see over here? If the tails of the distribution are extended beyond a certain limit, then they will run parallel to the horizontal axis, which means anything beyond Z is what we should not be considering. That's why we consider something which is within the values of A to Z, and that's why we simply call it Z. So it's the decisive variable. Why is it called a variable? I don't know, but it's actually a calculation. It is actually a calculation which talks about Z being equal to, at any point in time, for any normal distribution, this is true, x, you minus that x by mu, you take any value of x minus that value by mu, and then you divide it by the standard deviation. So this is the definition of that random variable Z. Z is also a standard normal variable or a standard random variable. It is actually a calculation methodology. So if I take any value of this and try to compare with any other value, I get a property, and that is the property which is going to be point number 5. Now, before I go to the property, what I mean by any value compared to another value, x is a random variable in the range of real numbers minus infinity to plus infinity, right? If that's the case, then it can assume any value within that range. Then I can replace this x with any value, and then for that range of numbers that I have, I can take the mu and the SD. If I put that number over here, I see the distribution, okay? Or I put the combination of mu and sigma square or mu and standard deviation into a function, and then I come to know about the probability density function, which is a normal curve, which is a bell curve. The property it represents is that at any point in time, if it is really a normal or a normally distributed variable, then mu is equal to 0 and standard deviation is equal to 1. So this is the golden rule. You can call this is the golden rule. The golden rule of any normally distributed random variable is that its mean is equal to 0, its standard deviation is equal to 1, right? If these properties are met, then we have a standard distribution. Now, we know that the mu, the average, can never be 0 for any real number. Can the average of heights, if I calculate heights of 10 people, not even 10 people, if I take the heights of all the people in this class, will that be 0? The answer is no. But then why is this rule saying that mu is equal to 0, SD is equal to 1? It's because it is basis the PDF. On the probability density function on y-axis, we have the probability or the density of the probability. And on the x-axis, we have the range or the histogram basis some class interval, irrespective of how small, how big the bins are. And then we simply join the dots to create the PDF. It also has a formula, which I said I'm going to share. And just to keep you informed, the PDF formula for each and every distribution is going to be different. So it's not the same for all, right? Now, we don't even have to remember it because we already know we have functions, but it's good to know because that function takes into two inputs. It takes mu and the sigma square, which is just the variance. And then it's going to take two constants, pi, and it's going to take another constant, which is epsilon. Epsilon is not really a constant, it's kind of a formulation in the logarithm scale. And basis that, it's going to calculate, it's going to draw the PDF. But if you draw the PDF, it is always, if it looks something like this, then this value which is interacting over here is 0. And every increment over here, every change of rate is by the value 1. So you can clearly say you have a range of numbers which is 0, 1, 2, 3, 4, or maybe -1, -2, -3, -4 on the left side, and on the right side, let's say I have again 4 numbers, 1, 2, 3, 4. If I have a distribution, if I have a random variable which is within the range -4 to +4, right? And then the numbers are changing by 1, then I have a normal distribution. So clearly, this is just a very, very simple or very toy kind of an example. But if you draw the distribution, on the y-axis you have PDF. On the x-axis, on the middle point, on the intersection of the peak, we have the mean, right? So this is the mu, and the mu is here. Okay, it is not the value here. So this value, if you plot it over here, let's say this is y of I. This y of I is not equal to mu. Okay. Y of I is simply representative of the top section of this graph or the PDF. So this is the PDF. Okay. Now the peak of the graph, if plotted onto this bar, onto this x-axis, is going to represent 0. So ideally, we should be represent a normal distribution like this. This should be the axis, and this should be how it goes. Right? This is going to be the normal distribution. Now you can see cases where people will define normal distribution as something like this. There will be cases where people will define a normal distribution being something like this because it is horizontal. It is at least meeting some of the criterias. Okay, some of the criterias are met, 1, 2, 3 are met. Okay, but that does not mean that it is really a normal distribution. If it is a standard normal or a standard Gaussian distribution, this rule must always be followed, the golden rule. The golden rule must exist. Okay, now this golden rule is going to be very confusing. Okay, when we look into the examples, we will come to know that golden rule, or the rule that I have defined over here, mu is equal to 0, s is equal to 1, is purely basis the use of PDF and not basis the actual numbers. Okay, let's take some examples and then we will be able to understand. Once we take the examples, if you have any questions, please do let me know. But looking through the examples is going to really help. Now, let's say in many cases, or maybe even I have myself eaten that as well, we bring boxes to our house of breakfast cereals, okay, like let's say Chocos and all these things. So let's say that somebody is the manufacturer of this breakfast cereal, and any let's say any standard box of that breakfast cereal. Okay, so I'll just write this as an example. So in this example, I'm going to take the example of breakfast cereal. Okay, this breakfast cereal, any standard box, okay, any standard regular box in the market, the company claims, okay, this is the company claim. I'm not saying this is the company claim. I'm the user, I'm the consumer. They are saying that on an average, the weight of this box is going to be 0.295 kg, right? So 0.295 kg is the scale in which they have taken. So that's why 0.295 kg is the average weight. And they're saying, yes, we are humans, we can make mistakes as well. So the standard deviation is going to be 0.025 kg, not more than that. So this is the claim of that company. Okay, any XYZ company selling breakfast cereal, they are saying any standard box you pick up, 0.295 kg will be the average weight of that box, or average weight of the items which is there in that box. Okay, it is not the weight of the physical box itself. It's like the cereal which is there inside, which you are going to buy. You are going to go to your home. You are going to put it into milk, and then you are going to eat. Right now, it's a very important thing to consider. Why? Because if people find out that this is not actually the weight, if there are boxes where 0.295 kg is not being sold to you for XYZ money, then you will get angry, and then you might write some kind of bad reviews about the company, or you might write letters into the consumer forum. Even worse, you might stop buying that product itself. You may go to some other vendor. So to find out whether this is really the case is going to be the challenge, or the concept behind our question. So the first question I have: what is the probability that the pack, okay, or any standard box weighs less than, okay, less than 0.280 kg, right? The company is claiming that I have 0.295 kg. I have taken a random value. I am saying no. They are saying they are saying it is 0.295 kg. I don't really trust them. We are human beings. We are bound to make mistakes. But what is the chance? What is the chance that we are, let's say, I have taken a value of 0.280, right? So it's like 0.015 kg less than the claimed value, right? The next question is, can this happen on the other side as well? So let's say, what is the probability that the standard box weighs more than 0. I don't know, 350 kg? Is there any probability that the box does not weigh 0.295? It is actually more. It has more content. And if there is, then maybe we would like to know what is the probability. Then a kind of a general question. I don't want to blame the company. Okay, I know that obviously there can be mistakes. So I will take this range. Okay, I will take weighs in the range of, let's say, 0.015 I don't know, 0.260 kg until 0.340 kg. Sorry, this I will say 0.340. So this is my lower limit 0.260 and my upper limit is 0.340 kg. Okay, so what is the probability that either it is less than 0.28 or it is greater than 0.35 or it is within the range of this? So I have these three questions. How can we answer this using the usage of the Z score? Or is this really a normal kind of distribution? Let's see. The standard distribution of the data does not match. The mean of the data does not match the criteria. Right? In this case, how are we going to identify that whether or not this is really a standard distribution or not? We have to plot the PDF. If we plot the PDF using mu, which in this case is 0.295, and standard deviation, which is 0.025 kg, we have to plot it using sigma square. This is sigma. So we have to take a square of that value. And then we have to feed that into my PDF function. And then the function is going to return me with that chart. If that chart is a perfect bell curve, then yes, it is a normal distribution. So the importance, what I wanted to convey over here is that without visualization, there is no other way to come to know whether it is a normal distribution or not, unless we try to calculate the Z score. If I try to calculate the Z score, then maybe I will come to know whether it is a normal distribution or not. Right? So let's see. Let's say what is happening. So my first question is, sorry, I'll take a different thing. My first question is, I have a distribution of the data. Let me not, okay, I have only 10 minutes, fine. Let me not draw like this. Let me clear it, because anyways, the y-axis is not going to make any difference, right? I know that y is the probability density function, but in this case, I will have to put it into the PDF formula and then I'll have to calculate. So rather, let me make it in a very simple way. I'll take the x-axis rather, and then what I will do, I will take the distribution of the data. Okay, so let me take the distribution of the data itself, not the PDF, the data. So if I take a distribution of the data, and if let's say I will assume that it is a normal distribution, assuming it is a normal distribution, how do I find the value of this? This is already given to me in my question itself. Question number 1 says this value is equal to 0.295. With the speed that I'm drawing, I think I will only be able to solve the first question, but let's see how we can go. So this is the mean, right? Now what is 0.280? Somewhere here. Okay, let's say it is just a small assumption that it is somewhere here. So this is, let's say this value is 0.280. If this is 0.280, then my first question says, what is the probability that I pick up a random box, standard size of that breakfast cereal, and it falls in this range? So this is what my area of interest is. Okay, this is what my area of interest is. Always try to visualize this in form of area of interest. Why? Because this is on this side. Okay, if this is the mean, and we are going to talk more about the sides. I don't want to define the sides. There is a proper name to that arrow that I have actually drawn over there, but it comes with respect to another statistical test that we are going to do. Here we are doing the Z test. So here we are going to find out the Z score or the value of Z. That's the reason why we call this a Z test. Okay, this statistical test that we are doing is also known as a Z test because we have assumed that is a normal distribution. How have we assumed? Okay, that is also a very important thing to consider that I will tell you, don't worry. But let's assume for this point in time that somehow I have come to know that this is a standard normal distribution. Maybe I have plotted the PDF and I have come to know. Now, this is the area of interest. What is the probability that it's going to fall in that area? So using the Z test, using the Z score, I can find. Okay, what is Z? There is a numerator, there is a denominator. The denominator in this case is the standard deviation. I know from the question itself, standard deviation is equal to 0.025. Right? So that goes into the denominator. And then on the numerator, maybe I'll take a text here. Okay, in the numerator, just a moment. Okay, let me go with pen only. It's fine. So in the numerator, I'm going to have the value of x. So the value of x is this. This is the tipping point. One of the values of the random variables, which I'm going to call the tipping point. So this is the mu, and this is the tipping point which I wanted to test. So this is my value of x. This is the random variable, 0.280 or 0.28. Then I minus that from I minus the mean from there. So it is 0.295. Okay. There is a dot here. So 0.28 minus 0.295. This comes approximately, if you do a calculation, minus 0.6. Right. So assuming this is a normally distributed data, or by finding the case that if I am taking the data set and then I'm calculating the PDF, if I see there is a normal distribution kind of a pattern, I can simply apply this formula and I can test any validation. So any probabilistic validation can be tested like this. I take the random variable which I am interested to know, which is the tipping point. I feed the mu and I feed the standard deviation. If I have the variance, I convert the variance into standard deviation. How? I take a square root. And then I get this value. If I get this value, right, then the probability is what? The probability is clearly something to do with this value of minus 0.6. Right? So for that, we need to calculate the z-score. Right? So this entire process is known as a z-test. So we have to calculate the z-score. And for that, I will need to use Excel. But if I'm going to use Excel now, we are going to run out of time. So we have calculated the value of Z. We have not really concluded what is going to be the probability. Okay, mind it, the value that I have got over here, which is, let's say, minus 0.6, this is not the probability. This is just the Z value. This is just the value of Z for any random variable. Right? So this does not define the probability. I'm not saying there's a minus 0.6 means I'm going to simply multiply this minus 0.6 with 100, and that becomes the percentage probability of any box which is going to be having the contents lesser than 0.280. Right? That is not what I'm saying. This is just a Z value. This is just a number, an arbitrary number that I found out using a mathematical formula which involves the random variable, the mean, and the standard deviation. Now I'll go back to Excel, or for that matter any other tool. Right? I go to any other tool and then I'm going to figure this out. Then I'm going to find out how I can make use of this minus 0.6, and then I can find out what is the probability. So when I find the probability, I convert that into a percentage and then I can see. Right? I don't think we are going to have time to do this because we just have a minute left. So maybe I'm going to clear all the drawings. And so this is it. As of now, this is what we have done. We are going to look into that at a later stage. In the next class, maybe we are going to take an Excel sheet and then we'll calculate. But these are very important. The features of a normal distribution. This must always be kept into mind because, as I have already told you during the start of the class, it is our aim, it is our goal to bring any distribution, which is either a Poisson distribution or it is a binomial distribution, in the form of a normal distribution, because then only we can apply a lot of statistical techniques. And there are ways in which we can bring them. Right? There are statistical ways in which we can bring any distribution over to a normal distribution. Right? We are going to look at those things. Okay, don't worry. This is almost the end of the probability scenario that we have looked into. Okay, yeah, yes, Alex, I just saw your question here. We assumed it is a normal distribution only to solve the problem. Right? I'm not going to tell you how we did that. Right now, it is not going to help you because if I tell you, you'll get confused. So there is a way in which I actually define that it is a normal distribution. But upfront, if I would like to assume, I can look into the distribution of the PDF. And looking at the probability density function distribution, I may want to assume only by looking at it, right? Only by looking at it, I may want to assume that this is the case. This may not be the case. Whatever I am saying may be wrong. But there is a process. I can apply that process, and then I can find out if any distribution of any random variable x is going to be normally distributed or not. But we are going to look into that, right? So don't worry.
Okay.
Okay. I think that's all. As of now, we don't have much time to continue. So let's make a stop here. We are going to continue tomorrow. Yeah.
Thanks, Bhavik. Nice session.
Thank you so much. Thank you.